You go to this anadim.com. And I have shared a link, no, in Teams.
Anadim.com. Okay.
ANADIGM, anadim.com. Then support, click support once.
Click support. Okay. Then
Once again. Again, support.
I already clicked support.
Download center. Again, support, download center. Anadim designer 2.
Oh. Download center. Okay. Download center. Then Anadim designer 2. Yes.
Yes, key generator. Key generator once click.
Where is it? Start key generator. Okay. It is asking for user ID and password.
Yes, yes. You have to create your own user account to generate a license.
If you are logging, if you don't have an account, you can get one now by clicking on this link.
Yeah, submit it. Oh, yeah. Submit. The same mail ID, right?
Yes.
Oh, okay, submit. Now check your mail once. You may get it.
The license key is only for single time use, or we can use this key for multiple systems.
You can use you can use the same license for multiple systems.
Okay. Installation of the first software is complete. So should we proceed to the second one?
Yeah, okay. You can install that software. And one more driver is there, no? CP21. Install that one.
Yes.
Install. Okay.
Okay.
That's all.
The installation is complete.
The hardware, no? You have the hardware, right, in your hand. FPA board, power supply, and then USB cable will be there.
Wait. Are you able to see the screen now? I have shared.
Yes.
Okay, now you can continue with the connection and what we need to do. We have both the oscilloscope and the FPGA board also. Now you can proceed.
FPA board, you take up that board.
Okay.
Adapter will be there, power adapter, and then USB cable will be there along with the board.
Both are same. This one.
Yes, yes.
Both will.
Okay. Now you open the wrapper, take the board out, and connect the power adapter. Better use that one cover. You just thrown out. No. Anti-static cover. Better you use that anti-static cover.
Antiseptic cover, which one?
Anti-static cover in the sense one with that how can I say that silver color kind of one shining color, transparent cover one. That one. That one.
This one.
Yeah, this one. Always keep on top of the on that cover only.
In this way, you are saying?
No. Like use that cover whenever you are using that board. No, better use that cover. Don't touch the board with your bare hands.
Okay.
Okay.
So how you will add the adapter then? It will. I will wrap this with the plastic.
Yeah, you can touch that. No issues. Now, that is USB cable, right?
Yes.
USB cable is connected to that USB adapter. I mean, USB socket is there no, on board. Yeah, same that one. Connect that and connect it to the PC. Other end you connect it to the laptop or PC, whatever.
Okay. The other end we will connect with the laptop. Right?
Once it is done, you connect the power adapter.
Yes, done.
Yeah, you connect the power adapter.
Connect the power adapter. Where is the connection? There, this one, right?
Next to that green color connector, the black one.
This one.
Yes.
Yes.
Can you see
done.
the turn? Turn on the board. I mean, turn on the adapter switch.
Turn on. Okay.
Yeah, power it on. Can you see the green LED?
Yeah, 2 minutes.
Now it is on. Okay. Now you go to your PC. I mean, in your PC, open the Untitled Designer software.
Okay. Untitled designer. This one designer tools of this.
This is really a tool for this FPAA tool. Okay. Continue with the default.
Then continue default.
Now you maximize the screen and then go to settings.
Settings.
Preferences.
1 minute. Setting preferences. Okay. Port.
Port it is showing COM5, port 5, right?
Yes.
Once you cross check with your PC, I mean device manager in your PC.
Device.
Ports and the tab. Now it's COM port 5, right? Now it is matched. Okay. Close this one and click OK. Apply and OK.
Select the apply and OK.
baud rate or packet size.
What about the serial baud rate, packet size, delay between packets?
Be the default values.
Awesome. These are default setting. Okay.
Go to target and toolbar.
Can you please
Yeah, target
Yes.
in toolbar window.
target?
Target. Display board information.
Clipboard. Yes.
You should get that. Yeah, all 4 FPAs are showing. So now your board is the connection has been established between your PC and PC and your hardware.
Okay.
Okay.
So this
On
is
the,
this board version and chip information is just to see whether this FPGA board is connected with the PC or not properly. Right?
FPA has a hands. Yes, I mean communicating with your board. I mean FPA board is communicating with your PC.
Okay.
Now all 4 FPAs are showing 1, 2, 3, 4. If you check your board, you will have that 4 FPAs.
You can check. Can you tell?
4 ICs can you see on the board? 4 ICs.
1, 2, 3, 4.
Yes. Okay. 1, 3, 4.
Yeah. Yes.
1, 2, 3, 4.
Yes.
This is U1, U2, U3, and U4 markers.
U1, U2, U3, and U4. Okay. So now connection has been established. Shall we start the intro? Do you have any idea about FPA? What is FPA?
No, we want to start from the beginning.
Okay. So the hardware you are having, no FPA hardware. So manufacturer of this hardware is Anadim Incorporation. It's a US-based company.
Yes.
So as you know, so they are the manufacturers of this FPA products and FPA IC and FPA board, everything. They are the manufacturer. Okay. So as we already know, so I'm from Opila Microsystems Private Limited. So we are a hardware and embedded software company in Bangalore. We are based at Bangalore. Okay. So as I already said, Anadim is the manufacturers of this FPA products. They are based in US. Okay. We are a design, technical support, and sales partner for this Anadim products. I mean, exclusively for this FPA products in Asia region. So we have introduced this FPA solution to various industries around India. And we have supported various engineering colleges to set up their lab with this FPA kits, FPA educational kits. Okay. So main purpose, am I audible?
Yes.
Yeah. Main advantage of this FPA, I can say, is we don't need data converters. You might have worked with DSPs, right? DSP boards, DSP development boards. Boards. So in this FPA, we don't need data converters. You have any idea about the data converters? Analog to digital converter, digital to analog converter. Any idea?
Yeah, a little.
A little like. So data converters are nothing but so if your processor is handling data, I mean processing everything in a digital domain means we have to feed the input in digital as well. We can only feed a input as a digital format, in digital format only. Okay. So for example, if we are using a DSP board or how can I say DSP board or microcontroller or microprocessor, whatever. So we have to feed data in a digital format only. But in this FPAA, we can feed everything in analog format. Okay. So current nowadays people are using DSPs, microcontrollers, microprocessor to process even the analog signals also. So this FPA is eliminating the need for this data converters because FPA is taking the input in analog format and processing everything as a analog. Format, processing everything in analog format only. So you will get output in analog format as well. Okay, input is analog, processing is analog, and the output is also analog only. So we can eliminate the use of this data converters. So the cost and power can be saved by eliminating the use of data converters. And working with DSPs, as I already know, DSPs are used for processing, signal filtering, and signal conditioning. And PID controllers can be implemented inside the DSP. So everything can be, whatever the DSP do, everything can be done in FPA as well, but in analog format. That is the main. Okay. So preliminary signal conditioning. So here preliminary signal conditioning and ADC will be there. It will convert that analog input into digital input, and DSP will process, and again DSP will be used to again it convert back to the analog format. That output to be converted to the analog format. Field programmable analog array. This is like a bird's eye view about programmable analog array. So what is field programmable analog array? So we can call this FPA, field programmable analog array, as a digital equivalent, analog equivalent to FPGA. I hope you heard about FPGA, right?
Yes.
Have you worked with FPGA ever?
No.
No, you have not worked, but you have heard about FPGA, right?
Yes.
You have idea, you have fair idea, or like a little idea you have about FPGA?
No, not exactly.
You don't know. Okay. FPGA is same as just a signal processor like DSP, not exactly DSP. It's like a signal processor. We can feed signals in a digital format and it will process your signal and gives the output. Okay. So FPGA can be configurable. Okay. When runtime itself, FPGA can be configurable. So same way, FPAA. So FPGA is a field programmable gate array. Okay. That is for digital processing, digital signal processing. And FPAA, field programmable analog array, is for analog signal processing. Okay. You will feed the signal in analog format and process and gives output as an analog format only. We can call FPAA as a simplified analog design. So basically, you can call FPAA as an analog equivalent to FPGA. Okay, not exactly FPGA. So FPGA have more resources. You can design a very complex circuits inside FPGA. It does have very, huge resources inside the FPGA. But in FPGA, resources are limited. But with that limited resource itself, you can design a complex circuit. Okay, and we can call this FPGA as a simplified analog design. Okay, why we call this simplified analog design? I'll just explain it later in the coming sessions. And it can be dynamically programmable during runtime. So what is dynamically programmable? So I'll just test the word dynamically programmable once again. So you have any idea about dynamic programming? Hello?
Yes.
You have any idea about dynamic programming? Dynamic programming?
No.
No. Okay. Dynamic programming is a thing, but okay. Once we have made one system. Okay. For example, simple inverting amplifier, you have made it. Simple amplifier. Just we are feeding one simple sinusoidal signal as an input. Just a 2-volt DC signal as an input. And we have made one system that can amplify your input signal and gives the output. Okay. So my amplifier gain is 2 volt. Okay. So my input signal DC voltage is 2 volt. So I'm feeding it to that amplifier stage. Output I'll get 2 is the input signal and 2 is the gain. So I'll get the 4 volt as the output. So it will be amplified. My signal will be amplified. Okay. So now, so the system is ready. So you have fed the, we have, now our system is ready. Our amplifier system is ready. We are feeding the input signal continuously. So for example, if I want to change the system's gain, okay, when the system is running, when the actual process is going on, if I want to change the system's gain, that amplifier's gain, you can't do in microcontroller or microprocessor, wherever. Okay, but in FPAA and FPGAs, you can change the gain by using some external controls or through PC. Okay, when the system is running itself, when the system is in runtime itself, you can modify the system's parameters. For example, if your system is an amplifier, you can change the gain of the system, gain of the amplifier when the system is in runtime. And just take again.
During the runtime.
During the runtime itself, we can change the system's parameters. For example, our system here we have assumed our system has amplifier. So most common parameter of the amplifier is gain. Okay, so I can change the gain of the system when the system is in running condition. Okay, irrespective of the input. Okay, input can be changing or it can be fixed. Okay, irrespective of the input, we can change the system's gain. Can you understand? Can you follow me? Hello?
Yes.
Yeah, okay. Irrespective of the input, we can change the system itself, system's parameter itself. Okay. So for example, you are hearing some song, okay, so that song is very noisy, okay, like you want to filter that song, okay, you want to filter that noisy sound, you want to eliminate the noise from your actual audio, okay, you don't know that noise, you don't know the noise frequency, okay. That time what you will do, so input is changing, input keeps on changing, okay, that noise frequencies keep on changing, you are feeding it to some filter, noise filter, okay, it will eliminate the noise and it gives the output actual sound, actual audio, okay. You don't know the frequency of the song, sorry, you don't know the frequency of the noise. How can you eliminate that? Like I can change the parameter filter frequency dynamically, so accordingly it can cut off the noise and you will hear the actual audio. Just a simple real world example I'm telling you, okay, to understand, to better understand this dynamic programming concept, okay. So dynamic programming is nothing but irrespective of the input and out, irrespective of the input, you can change the systems parameters, okay, based on your application you can change the system parameters so that it can actually adjust with the input and gives the output. So dynamically you can run time, you can change the parameter of the system. So this is dynamic programming concept. Any doubt in this?
Then why it is called simplified analog design?
Simplified analog design, I'll tell you that later.
Okay.
So next slide I'll tell you that, I'll come back, okay. And it is very easy to learn, and drag and drop EDA tool, drag and drop in the sense inbuilt blocks will be there, it is just a drag and drop tool, and it can generate a C code, okay. So in a microcontroller, DSP and all, you have to write your own C code or Python, whatever the programming language you take up, so you have to write the code, okay. But here it is FPAA EDA tool.
Hello.
Come again.
Once I just make my block, then it will automatically give me this a Python code or C code for that.
Yes. Once you have finished your circuit, okay. So for example, in this, in the
Python directly by taking that code.
Yeah, you can dynamically program. You can take that code and you can just modify your code based on your application. So this is generating C code. So we are generating C code that is used for dynamically programming the FP.
Python code also.
C code only, not Python code. Gave explanation. This example I gave you as Python, but C code only it can generate. So if you see this image, so we have designed a simple circuit, this inverting amplifier circuit. Okay. If you can design a complex circuit also, it can generate a C code. You don't need to write a C code. You can modify the code in such a way it can dynamically dynamically update your system parameters. Okay. And in inbuilt a simulator is available inside the EDA tool itself. Inbuilt simulator is available. You can monitor four channels of signals simultaneously. Can you see? So this is a probe. Okay, you can monitor. So this is the inbuilt oscilloscope, inbuilt simulator. Oscilloscope is there. You can monitor 4 channels simultaneously: channel 1, channel 2, channel 3, and channel 4. And channel settings are there, volts per division. So as like oscilloscope. Okay. So volts per division is there, position is there, how many voltage you are getting. You can use the cursor and you can save the waveform. Lot of lot of features are there. So I'll explain this when I'm take that EDA tool session. And
Okay.
top down up, we call it. Yeah. Come again?
No, okay.
Okay, no. Okay. So I'll just summarize the introduction about FPAA once again. FPAA is field programmable analog array. We can consider this as analog equivalent to the FPGA. Not exactly FPGA, but we can consider this as analog equivalent to FPGA. Resource wise, FPGA and FPA have some differences, and but in processing wise, it has a lot of similarities. So we can call this FPA as the analog equivalent to FPGA. Okay. And this is simplified analog design. I'll explain this later. And dynamically programmable during runtime. We can change the system parameter when the system is in running condition, when the system is in on condition. When some process is going on, we can change the parameter of the system. So it can adapt to the environment, environmental input. And it is easy to learn, and it can generate a C code for your whatever the circuit you have designed. You can generate a C code and you can dynamically program using that C code. Any doubts in that?
No.
So far you have understand, right?
Yeah.
Okay. This is a product differentiation with dynamic reconfigurability. So what advantages? Basically advantages of dynamic reconfigurability feature. So you can design a products that can adapt to the environmental input. As I just now before a while I said no, it can adapt to the environmental input. When we tune the system parameter, when we change the system parameter when the system is in running condition. And also we can design a product that can change the functionality of the circuit sequentially over time. So different, dynamic reconfigurability has more advantages. I'll explain it later. So just for introduction, this is enough. And the accuracy of this FPA is 0.1 functional, 0.1% functional accuracy is there. And the chip-to-chip accuracy is also plus or minus 1%. What does this functional accuracy means? So when you take up a single FPA chip on board, on this FPA board, you have 4 FPAs, right? 4 ICs. So that single FPA, if you take up, so that functional accuracy of that particular single FPA is 0.1%, plus or minus 1%. And this chip-to-chip accuracy, so like when you process the same circuit in different two different FPAs. Okay, so the accuracy between these two adjacent FPAs, adjacent whatever, so like out of this 4 FPA, you can process, you can design a simple circuit in any FPAs, any two FPAs. So accuracy would be plus or minus 0.1%. Okay, so drift-free performance, immune to process, temperature and aging. These are also advantages of this FPA. So simplified analog design, you can reduce the time for analog design implementation. So you have idea, right? And that in linear integrated circuits laboratory, electronic circuits laboratory, you have to spend a lot of time to design a simple circuit, right? Like you will take up op-amps and those passives, capacitors, resistors to design a simple inverting and non-inverting amplifier, simple circuit itself. You have to spend a lot of time. So, okay, but in FPA, the process of designing a simple circuit, I mean, even a complex circuit can be simplified. Okay, so it can save your time, and you can so design time can be saved, and you can actually focus on characterizing the circuit. I mean, characterizing your design, how it behaves and how it works. Okay, those things you can just focus instead of designing. So basically, it can reduce the design time. And this is Anadim Designer overview. So easy to use PC-based software. So an intuitive drag and drop user interface is there. So if you open this Anadim Designer tool, inbuilt blocks will be there. Okay, library will be there. In that library, so most of the analog functions, can you tell me some basic analog functions have you worked with? Previously, you have worked with in linear integrated circuits laboratory. You have worked with inverting amplifier, non-inverting amplifier, differentiators, comparators, integrators. You have worked with, right?
Yes.
Those you have. So in your traditional way of designing this inverting amplifier, non-inverting, whatever, okay, those simple analog blocks, you will use physical components, right? Op-amp and this capacitor, resistors, everything you will use to design a simple circuit itself. But here in this FPAA, so ready-made blocks will be there. For example, this is inverting amplifier. You can take this inverting amplifier from the library and place it inside the FPAA and give the connection, feed one input to this inverting amplifier, and you can check how it behaves, how this inverting amplifier behaves. You can change the parameter of the inverting amplifier. Amplifier in the sense gain, you can change and see how it behaves. Like, and also filters, a lot of filters are available. Different filters are available. Band pause, band stop. Almost all the analog functions will be available as a ready-made blocks in library. You can go to the library, you can take up those functions and use it. I mean, according to your application, according to your needs, you can use any functions from the library. So I'll just list. Okay, and as I already said, built-in signal generator, built-in oscilloscope is there. Built-in signal generator is also there. You can see here. This is a signal generator. Signal generator, you can use it for simulation purpose only. Okay, so if you want to check the output in real time, you can use an inbuilt oscillator. Inbuilt oscillator is there, and this is inbuilt signal generator. You can use the signal generator for simulation purpose. Okay? And discrete time simulator is there. Extensive help documentation is available for all the inbuilt functions. Extensive help documentation is available. How this particular function has been implemented, how you can use it, what are the functions available, what are the parameters available, what are the features of those parameters. Everything has been given in this help documentation. Configurable analog modules. What is configurable analog modules? So can you follow me so far?
Yes.
Yeah, okay. So now we'll move on to the next session, next topic, configurable analog modules. What is configurable analog modules? So I don't know, the inbuilt functions, inbuilt library functions are available. Okay, that integrator, differentiator, filters, amplifiers, those functions we call it as configurable analog modules. Okay, CAM, configurable analog modules, or CAM we call it as. Okay, these are the different functions available. This is one amplifier, and this is a kind of a filter, and this is a periodic waveform generator. Customized waveform can be generated by feeding some Excel data. And these are oscillator, and these are filters, integrator, differentiator. Most of the analog functions will be available. So we can call these analog functions as a CAM, configurable analog modules. And help documentation is available. This is a parameter window, like property window. You can double click that particular CAM module and change the parameter of that module. This is parameter window. I'll explain this later. So CAM is nothing but inbuilt analog functions. And dynamic programmability, I already explained it. It can generate a C code. So an Apex 3.3 volt architecture. So important thing is this operating voltage of this FPAA board. This FPAA IC itself is 3.3 volt. So more than 3.3 volt, it can't accept. The maximum operating voltage is 3.3 volt only. Okay. And this is FPAA IC. Single FPAA. This is not FPAA board. FPAA IC. You have 4 FPAA ICs on board, right? And each FPAA. Sorry?
This is one.
This is each one. Single FPAA. So architecture of a single FPAA. Okay. Inside this FPAA, we have CAB, CAB1, CAB2, CAB3, and CAB4. Okay, what is CAB? So previously I told the CAM. What is that?
Configurable
analog module.
Configurable analog module is inbuilt analog functions like amplifiers, differentiators, those inbuilt analog functions is configurable analog modules, that is CAM. And this is CAB, configurable analog blocks. Okay. So inside FPGA, you will have that logic gates, right? Inside FPGA, you will have a logic gates. Same as that, inside FPGA, we have analog blocks, configurable analog blocks. 4 analog blocks are available inside FPGA. 4 analog blocks are available: CAB1, CAB2, CAB3, and CAB4. Okay. So on top of this analog blocks only, we are placing a CAM. So like configurable analog block is nothing but it's resources inside the FPGA, available resources inside the FPGA. Okay. Inside each CAB, we have 2 differential op-amp, 1 differential comparator, and 1 ADC, and 8 programmable capacitors will be there. Okay. Inside each FPGA, we have 4 CAB, configurable analog blocks. Okay, CAB 1, 2, 3, 4. And inside each cab, we have 2 op-amps, differential op-amps. Okay, and 1 comparator, differential comparator, 1 ADC, and 8 programmable capacitors. So if you consolidate all 4 cabs, we will be having 8 differential op-amps. Inside each FPGA, we'll be having 8 differential op-amps and 4 comparators, 4 ADC, and 32 programmable capacitors inside each FPGA. Okay, up till this, all the resources are getting exhausted, you can design as complex as circuits as possible. Okay, so once the circuits has been, and these resources are exhausted, you can't design more. You can't use any more. Okay, you have to go for next FPA, adjacent FPA. You can cascade those two FPA, like output of this FPA1 can be given as an input to the FPA2. So you can cascade those adjacent FPAs and you can design a much complex circuits if your application demands. So two things. One is FPAA. Inside each FPAA have 4 cabs, configurable analog blocks. Okay.
And they are cascaded or parallel?
Sorry. It's
Four
cascaded. Cascaded.
Cascaded, no?
Yes. Each FPA have 4 cabs. Cab 1 to configurable analog blocks. Cab 1, 2, 3, 4. And in each cabs, okay, 2 op amps, 1 comparator, 1 ADC, and 8 programmable capacitors are there. Okay. And these are the IO cells. IO cells of FPA. Each FPA have 7 IO cells. Okay, IO cell is the nothing but input output cell. You can configure this IO cell as an input, either as an input and as well as output. Okay, that's based on your need. Okay, your application. Okay, 7 IO cells and 4 cabs. In each cab, you have these resources: op amps, comparator, ADC, and capacitor. Okay, understood, right?
Yes.
And one more important is a 3.3 volt architecture. The maximum operating voltage is 3.3 volt only. Okay, and this FPA is if you if you see that FPA board, 4 FPAs are there.
Okay.
On top of the FPA, can you see one more IC, like little bigger one? PIC, PIC microcontroller. Near that USB connector.
You are talking about this AC, okay?
Yes. That I was talking about that only. So that is PIC microcontroller. Okay. Why that PIC microcontroller is? So the FPA I was explaining, no, FPA, field programmable analog array, that 4 ICs. Okay. Hello. Yeah, that IC can only process the signal, like whatever the signal you are feeding, analog signal you are feeding, it can just process it and gives the output. It doesn't have any intelligence. Okay. So it needs a command. Okay. On its own, it can't work on its own. Okay. It needs a command from a third party intelligence, like intelligence in the sense it can be microcontroller, microprocessor, or whatever it is. Okay. So inside the microcontroller, we have to feed a program. Okay. So this microcontroller, onboard microcontroller, feeds the command, gives the command to the FPAA, do this. So FPAA will process the signals, analog signals, can give the analog output. Okay. So to give the command to the FPAs, all 4 FPAs, we are using one microcontroller. Okay. This microcontroller is communicating with our PC.
Means this microcontroller commands the 4
all 4 FPAs. Okay. So how this microcontroller gets a programming? Okay, this microcontroller is communicating with our PC through this USB cable. So you have connected one USB cable, right, between the PC and your board, FPA board.
Okay.
Through this cable, that EDA tool, okay, that Anadim designer tool is communicating with this microcontroller. So microcontroller receives the data from EDA tool. Okay, we are designing a circuit on the inside the EDA tool and we are feeding it to the FPA board. I told no that the right configuration data to serial port. Oh, I have not. Okay. Again, I meant to say that. Okay. That EDA tool will give data to the microcontroller, and microcontroller gives the command to all the FPAs. The FPA will get the data. Okay, input data. I mean analog data from outside world or inside the FPA. We can generate a signal, input signal. Okay. So FPA IOs are there, no? FPA IO cells, 7 IO cells.
Okay.
Through those IO cells, we can feed a input signal. For example, some sensor data we can feed. So through those IO pins, we can feed a sensor signal, and FPA will process based on the commands from the microcontroller. Okay. So the interface between the FPA and microcontroller is SPA interface. You know SPA? SPA interface?
No.
You know, serial peripheral interface. SPA interface is it's a protocol. Okay. You know any protocol, communication protocols?
No, sir.
No, you don't know. Okay. So SPA is a serial communication protocol. So that the protocol can help us to help 2 different devices to communicate between them. So we are communicating, no? So English is the so we are communicating in English. English is just a medium for both of us to communicate and react it. Okay, accordingly. So based likewise, this microcontroller and this what is that? A microcontroller and this FPA is communicating through SPA interface. It's like an interface. Okay, SPA is a protocol. So through that SPA interface, both microcontroller and FPA is communicating. Understood?
Serial port communication.
Serial port communication. USB is also a serial port communication like USB. So we have one more serial protocol is that is SPA. So SPA is a communication between microcontroller and your FPA. Understood, right?
Yes.
Okay. So I told you two things. FPA is a field programmable analog array. It's analog equivalent to FPGA. It can be dynamically configurable. Okay. And the cams are available in library. What is cam?
Configurable
Analog module.
Analog modules. So those are inbuilt functions, inbuilt analog functions, integrator, differentiator. Those inbuilt functions are cams, and the cab is also there. Cab is inside. I mean, resources present inside the FPA. In each FPA, we have 4 cabs, and each cab we have op-amp, comparator, ADC, and programmable capacitors. Okay, and it is a 3.3 volt architecture. So I'm just summarizing it time to time. I'm just summarizing it so you don't forget it. Okay, you will just follow me. Okay, and in each FPA you will be having 7 IO cells. Okay, IO cell 1, 2, 3, 4, 5, 6, and 7. 7 IO cells you will be having. Okay, so those IO cells can be used to feed the input and take the output from the FPA as well. Understood?
Yes.
So whenever you have doubt, no, you just ask me to stop and okay, I'll clarify your doubts. Okay. And these are DPASP application. As I already told, DPASP, we can call this FPA as a DPASP. So what is FPA? FPA is basically a signal processor. Okay, this is programmable. Okay, so we can use one more term for FPA, dynamically programmable analog signal processor. That is DPASP, dynamically programmable analog signal processor. Okay, these are the applications, simple applications of FPA. Okay, complex analog filtering circuits can be, analog filter circuits can be implemented. As I already told, so inbuilt filter functions are available. Okay, those functions can be used to design a complex filtering circuits. Okay, like complex filter circuits in DSP you might have studied Butterworth filter, Chebyshev filter, different filter techniques you have studied, right?
Yes.
And those filters can be implemented inside the FPA, can be designed, and you can check the output in real time. So it can be implemented. This Butterworth Chebyshev filter, inverse Chebyshev filter, I mean like Bessel filter, different filters can be implemented inside the FPA. And the sensor signal processing can be done. Sensor signal conditioning. Sensor signal conditioning is nothing but, I don't know, data converters. For DSP, you are having so we can only feed digital data, digital input data. But in analog world, our sensor data is analog in format. So what we are converting that analog data into digital format in such a way so DSP can accept that data accept the digital input. So that analog to digital conversion is there, no? That is one type of signal conditioning. Signal conditioning is that our processor, so we are converting a signal in a format that processor can take up. Okay, without any hassle. Okay, that is signal conditioning. Different signal conditioning techniques are there. One is linearization and data conversion, like ADC to ADC, DAC. Those are signal conditioning techniques. Lot of signal conditioning techniques are there. So that signal conditioning can be done inside the FPA. Okay, and closed loop control systems can be implemented. Closed loop control system is nothing but PID controllers, proportional integral derivative controllers. PID controllers, you know?
Yes.
In control system you have studied, right?
Yes.
Yeah. So PID controllers can be implemented inside the FPA. Filters can be implemented. PID controllers can be implemented. So I told you that ADC, DACs. ADC can be implemented inside the FPA because it does have inbuilt ADC as a library function. It can take the analog input and gives the digital output. FPA itself can give the digital output. It cannot take the digital input. Okay, keep in mind it cannot take the digital input, but it can give the
analog.
It can give you the digital output because inside ADC is available. Okay. And some more application areas. So this FPA can fit in different application areas. RFID application, different sensor signal applications, sensor processing, audio processing can be done. Okay.
And means we can record the sound.
Sorry, we can hear the sound. We can feed audio input to the FPA. Yeah, we can feed audio input to the FPAA, and it can process. And like we have one song, and we have one noise is there. You can feed a noise signal to the FPAA, and we can feed a audio. I mean song as an audio input to the FPAA. We can merge those two signals. Okay, now we can merge audio with the noise. Okay, output you'll hear a noisy audio. And one more thing is important thing is the FPA. Inside the FPA we can use different filtering. We can implement different filters. Chebyshev filter, as I already told, Chebyshev, Butterworth, I mean almost all different filters can be implemented inside the FPA. So audio signal processing, you can use different filtering techniques to eliminate the noise, add the noise. Like for as a demo, you can implement a different filters inside the FPA, and you can feed the audio input to those filters, and you can try changing those filter parameters. Like you can do anything. Like so, it can be useful for audio signal processing. Okay, it is one of the audio signal processing is one of the applications. That's it. And it is also suitable for biomedical signal processing. So why? Because these biomedical signals are, biomedical signals like heart signals and brain signals and muscle signals. Okay, these are the different biomedical signals. Those biomedical signals are very low in voltage levels. Voltage levels will be very low in terms of microvolt, millivolt. Okay, so this FPAA can take up the very low level voltages in terms of microvolt, millivolt. Those signals it can accept. The FPA can those biomedical. One more thing is those biomedical signals are also analog in nature. So if we convert that analog into digital, some approximation will be there. Okay, you can't get a same signal whatever you are getting from the human body. So if you convert that into digital format, some approximation will be there. So 100% it won't be the same signal. Some approximation will be added. Okay, so but in an analog, this FPAA, we are feeding whatever we are extracting from the human body, we are feeding it as it is. We are not changing at all. Okay, that biomedical signals can be fed to the FPAA. We can process, we can amplify the signal first. Okay, because very low in range, very low voltage signals those are. Okay, we can amplify it and we can process further, and we can get the output. Okay, so most important applications are sensor signal processing and audio signal processing and biomedical signal processing, because it can accept the two. So personally, I have fed 200 microvolt signals as an input to this FPA and amplify and process. I have done some simple processing of biomedical signals. My muscle signals have extracted and fed it to the FPA. I have processed. I tried processing. I mean, EMG's muscle signals and heart signals. I have processed different signals using this FPA. So these are the main application areas. Any doubt in this?
No, none.
Nothing. No? So okay. Gain the flexibility to adapt your design, simplify your analog design. So why? Because simplify your analog design in the sense all functions are pre-built functions. In the library, you can take up those functions and you can connect interconnect those, different functions, inbuilt functions. You can make your own circuit. So that's why I call it a simplified analog design. You don't need to scratch your head to design your system. So all functions are available as a pre-built function. You can just take up and interconnect it and make your system ready, make your circuit ready. So this is summary. So simplified analog design, dynamically programmable, as I told. So we can monitor and modify your system parameters when the system is in running condition. That is dynamically programmable. So it is easy to learn drag and drop EDA tool. Drag and drop is nothing but we are just drag and drop those inbuilt functions inside the FPA. That is drag and drop EDA tool. It can generate a C code. Okay, for your whatever the circuit you have designed, for that circuit it can generate a C code automatically. So you can use that C code to dynamically program your FPA. Okay. So this is a summary. Okay, this is Anadim Designer tool, EDA tool for designing circuits to be configured to configure FPA. Okay. Anadim Designer 2. Just double click. So I hope all your PCs are installed with the software, right?
Yeah.
Okay. Can you follow me? So I will explain the software EDA tool first. So features and how to operate and all. Later on, we'll do the hands-on.
Okay.
Okay, as soon as you open, you'll get a window like this. Okay, would you like to continue with default chip, choose a different chip, or view the tutorial? Okay, so you check. Okay, is it visible? Like, can you read this number?
AN 231E04.
Okay. So the same part number. This is the part number of FPAA. Okay, model number of FPAA. So currently we are using the same part number. Okay. On board, if you see on top of the FPAA ICs and the U1, U2, U3, U4 is there, right? So on top of that, you can see the same part number printed on. Okay, AN231E04. Okay. So the part number has to match whatever the FPAA board has should have, and our EDA tool also should have the same part number. Okay, AN231E04. Okay, so by default, AN231E04 is placed inside the EDA tool. So I'll go with the default chip, continue with default chip. If you have any other part number apart from this AN231E04, you can choose a different chip. Choose a different chip. For example, here if it is AN231E02 or something, it is there means just choose a
But
different chip.
the board, I didn't find AN20231E04.
Yes, AN231E04. We have
I didn't
AN231E04 on board. We have to choose the same in the EDA tool also. Okay, so if you see here, these are Anadim Vortex devices. If you see AN220, AN120, AN221, AN121, so different versions are available. Now we are using AN231E04. Okay, I'll just select this. You can select AN131E04 also. You can select.
One can select, there is some criteria on functionality that
Yes. Each IC is a different functionality, and you can see configuration. You can see, okay, this is static and this is dynamic. All the ICs are not dynamic in nature. Dynamic in the sense dynamically configurable. Okay, this is static configuration, and this one is also static configuration only. Okay, but our AN231E04 currently we are using that can be dynamically configured. Okay, and if you see cams, number of cams can be used. 49 inbuilt functions are available for this AN231E04. And voltage is 3.3. As I told, the operating voltage is 3.3 volt. Okay. So since we have the AN231E04 on FPA board, so I'll go with the AN231E04. Just click this, click OK. Okay, right? Okay. AN231E04 is selected now. And as I told, these are the IO cells. IO cell 1, IO cell 2, IO cell 3, IO cell 4, and 5, 6, 7. 7 IO cells are there. And this is digital IO cell. It does have, additional features are also there. Okay. And if you click this arrow, you will see the resources of FPA. I don't know that each FPA have 4 caps. Cap 1, cap 2, cap 3, and cap 4. And in each cab, we have one ADC, 2 op amps, and 1 comparator, and 8 programmable capacitors. Okay. In each FPA have 4 cabs, and in each cab we have this resources. Okay. Now you will understand how it works. I'll just click this get new cam toolbar. Tool in get new cam function in the toolbar. Just click this. You will get the library functions. These are the library functions available for this particular model number AN231E04. For example, I'll choose gain inverter, inverting gain stage. Okay, I'll just click and create cam. You'll get it like this. Just hover the mouse and place it anywhere inside the FPA, not inside, not on the IO cell, anywhere inside the FPA. Just click one single click. You will get a property window like this. There you can see clock, and this documentation is available. If you click this documentation, you will get the help documentation of particular analog function. You see gain off cam, gain hold cam, and how it has been built, how it is built, this particular function, how it is achieved. And these are the parameters, how C code is generated, I mean, C code functions has been given. So help documentation. So if you have any doubts, you can go through the help documentation. Close. And this is the parameter window. This is parameter. So I'm using a gain inverter, inverting gain stage. So most common only one parameter for this gain stage, that is gain. I can change the gain. I'll just click and make it 2 and enter. That's it. I'll click OK. Now the cam has come. I'll just drag and place it to the center. Okay. If I want to change the parameter again, just double click this. You'll get the parameter window. Again, you can change it to 1. Now you see the beauty. So previously, this was not highlighted. Okay. Now, if you see, if I click this, it is getting highlighted. Cab 1, this 4 capacitors and 1 op amp is getting highlighted. Okay, if I delete this one, again it is not selected. Why means this particular function, this particular analog function is using the resources available inside the cab 1. Understand, right? Hello?
Yes, sir.
Yeah, you can understand. As soon as I click this particular resources are getting highlighted. This 4 capacitors and 1 op amp is getting highlighted. Okay. If I delete this, it will go off. Okay. Why? Because this particular analog function I placed inside the FPA, I used inside the FPA was using this resources available in the cab 1. Okay. Understand?
Yeah.
Can you follow me?
But how if you want to change the cab 1 to cab 2, can we do that?
Okay, come again. Your voice is not.
Making cab 1.
Sorry, come again. Say it again. Your voice is not clear.
If I want to change from cab 1 to cab 2, is it possible, or by default it is taking for cab 1?
If you want to change the gain, it is possible or not? That's a question, right?
Not again. From cab 1 to cab 2.
Cab 1 to cab 2. No. You don't have a control over that. Okay.
That's what I'm asking. It is automatically on cab 1, right?
Over that. It will take up the resources automatically. We don't have a control over that.
Okay.
So if I place one more function, it is taking same cab resources. If I place one more, it is taking another cab resources. Why? Because this cab 1 doesn't have any capacitor left to use. So it is taking cab 2 resources. Okay.
Okay. So thing is, it will use the resources of cab 1 first. If it is full, then it will automatically shift to cab 1, cab 2, and then it will use the resources of cab 2, right?
Yes, of course. Okay. And you can check the power consumption also. You see, this much of power this particular function is taking 39 plus or minus 2 milliwatt is taking. So power resources you can check. And one more important function is, if I double click, so and there is no functions. There are no functions available inside the FPA now. Analog functions. Okay, I'll just double click inside the FPA. You will get a window like this. Okay, this is clock settings. Why clock for FPA? Because the FPA is working based on is implemented. This FPA is implemented based on switched capacitor technology. Okay, you know switched capacitors.
No.
Okay, switched capacitor is a technology where you can use switches and capacitors. Okay, so why switched capacitors? So switched capacitor technology, the name itself you can identify. It is a combination of switches and capacitors. Okay, why capacitors? Because capacitors can be programmable. So we can charge and discharge the capacitor based on the charging and discharging cycle. We can program the capacitors. We can change the values of the capacitor. Okay. So since we want to dynamically configure the FPAA, so we are using switched capacitor technology. We can dynamically program and erase the capacitor value. We can just program the capacitor, and after that we can erase the capacitor values. Okay, so the capacitors are getting charged and discharged continuously based on the input from the user. Okay, so by using the switched capacitor technology, we are dynamically programming the FPAA. That switched capacitor needs the clock signal. Why clock signal for switched capacitor? How fast the switches should be turning on and off. So switches means it will turn on and off alternately. Okay, how fast it should happen. So we have a control for that. We have a control over the frequency of the clock signal. So that switch is turning on and off continuously. So we have a control over that. That control is based on the clock signal. That clock signal we can we can set the clock signal. Okay, so if you see, we have FPAA board, right?
Yeah.
So next to the USB connector, you can you see silver color one small IC?
How much clock?
That is crystal oscillator. That is crystal. Okay, it can generate a clock frequency, and this clock signal is fed to the FPAs. So from that crystal oscillator, FPA is getting 16 kilohertz of clock signal. 16,000 kilohertz. Sorry, not 16 kilohertz, 16 megahertz. That is 16,000 kilohertz clock signal is fed to the FPAA. Okay, and so that 16,000 kilohertz is divided into two clocks. That is system 1 and system 2. This is clock divider. If you change the divider, automatically this clock output will vary, because you can see FC is nothing but FC by 70. You can see, so FC is 16,000 kilohertz. FC by 70 means the 16,000 divided by 70 is 228.571429 kilohertz. So if I change this, automatically this will vary. Okay, and from this you can see all these clock signals is varying. All the clock signals are varying. Can you see?
Yeah.
Why? Because here we have selected system 1, and here it is system 2. System 1 is selected in all 6 clocks. All 6 clock 0 to clock 5, all 6 clocks system 1 is selected. If I'm varying the system 1 itself, so all clocks are varying. Okay. Now if it's change the system 2, nothing is varying, because here the system 2 is not selected. If I select system 2 here, only this one will vary. Okay. Why this many clock settings? Because inside the FPAA we may use different analog functions. In a single FPA we may use different analog functions. So each functions may use different clock frequencies. Okay. To set a different clock frequency for each function, separate functions. Okay, we are using this many clock settings. Okay, this clock settings are used by the, for example, now the master clock is 16,000, and system 1 is also 16,000. System 2 is also 16,000. You can see clock 0 to clock 5. By default, I'll keep the clock 0 to clock 5 in a default position. I'll click cancel. Okay, I've not modified anything. I kept it as it is. Okay, now if I place one gain inverting stage, double click and place it inside. Now you can see clock A, clock 0 to clock 5. Okay, just now we have seen clock 0 to clock 5 in the clock divider settings. Okay, so whatever the clock you feed there, you set there, it will reflect here. Okay, the clock settings which we are, the clock signals which we are setting there is used by the CAMs. CAMs means analog functions. Every analog function is using those CAM settings, clock settings. Okay, for example, now you see clock 0 is 4,000 kilohertz. Okay, now I'll go there and change the clock settings. If I change this, now it is changed to 333. I'll click OK. Now if you double click, you see clock 0 is changed. All clocks are changed. Okay, so whatever you set there, it will reflect here. Okay, so based on the requirements, based on your application, you can change the clock settings. If you are dealing with higher speed functions, little high speed systems, you can set the clock frequency in a little higher. You can set the clock frequency little higher. But if you are dealing with a low speed system, you can set the clock frequency as minimum as possible. Again, it is based on your application demands. Okay, I'll delete it. I said three important things here. So FPA is based on a switched capacitor technology. So because capacitors can be programmable, so when you want to dynamically configure your FPA parameters, you can just close the switch. I mean, so you can just control the switch. Okay, alternate. So based on that, and the capacitor will charge and discharge. So we can dynamically program the FPAs. So FPA is based on switched capacitor technology, and another one is a switched capacitor needs a clock signals. You can double click inside the FPA and change the clock settings based on your requirements, system demands, I mean application demands. And one more is FPA resources, cab 0, cab 1 to cab 4. So whatever the cam you are using inside the FPA, it will take the resources of these cabs. Okay, you don't have a control over the cab resources. As once all the cab resources are exhausted, you can't use any more functions inside a same FPA. You have to place one more new FPA, and you can cascade, you can interconnect those two FPAs. You can interconnect those two FPAs and feed the output of this FPA to the next FPA, adjacent FPA as an input. That way you can design a complex systems. Understand, right?
Yeah.
Okay. Any doubts so far? Any doubts so far?
No, about the CAB and FPA, we don't have any doubt, but how to program it, that will be further, I guess.
Dynamic programming.
Yes.
Dynamic programming will start. We'll see tomorrow, because now we'll go with, initially we will start with basic simulations, and the real-time output. I mean real-time monitoring. Okay, I mean how to use the hardware and all. Maybe tomorrow afternoon we'll start dynamic reconfiguration. Now I'll design a simple circuit. I'll design a simple inverting amplifier. Okay, just click this get new cam toolbar. I'll close this. I'll open a new one. Continue with the default chip. Since I'm having a AN231E04 already, I'll continue with the default chip. Just click this get new cam. Select inverting gain stage. Create cam and place it. I'll keep the clock frequency as 4000 kilohertz. Set the gain as 1. Click OK. What I'll do is, so this is my system, inverting amplifier system. I have designed it. We need to feed the input signal and monitor the output signal. Okay. Now this is IO cell 1. Different functions are available in IO cells. Just double click inside the IO cell 1. As I already told, you can either assign this IO cell as an input and as well as output. And independent amplifier also you can select. Okay. Now just I will assign this IO cell 1 as a input. So this IO cell also have a documentation, help documentation now. If you click this, help documentation is available for every IO cells. Okay, how you can use the features available in the IO cell. We can go through this if you want. I will assign this IO cell as input, IO cell 1 as input, and click OK. Now click here and just drag and click here. Now this IO cell is connected to the input stage of this inverting amplifier, and IO cell 3 I'll connect it. Just assign as output. This output. Click OK, and just click, drag, and click it here. So now we have connected the IO cells to the input cell and output cell to the inverting amplifier, to the input and the output stage. Okay. Now we have to feed. We should feed the input signal. As I already told, as I said, so inbuilt signal generator is available in the EDA tool. Yes, this is create signal generator toolbar. Just click and here. So now it is sine wave. Just double click. We can select the type of waveform. Triangle, sawtooth, different waveforms are available. For example, I'll go with the sine wave of 20 kilohertz frequency and 1 volt as amplitude. Okay, this okay. Now I'll simulate. Let's begin simulation. So nothing I can see. Why? Because so we have created a circuit and fed the input. Okay, now we have to monitor the input and the output points. So without probe we can't monitor, no? So I'll choose probe, place one probe here and one more probe I will take. I'll place it in the output side. Now you can see this is input. So the pink one is input, 20 kilohertz, 1 volt sinusoidal input, and output is just inverted. Because my gain is 1, it is just inverted. If you see, just you can use the cursor available, inbuilt cursor available. You can check at any instant of time, both your input and output signals will be same. I mean, in amplitude wise, it is same, but it is inverted. Output is inverted. Since we are using inverting amplifier. Okay, you can see both are 0.68 and minus 0.68. Now I can change the gain. I'll make it to 2. And okay, now I'll simulate. Now you see it is minus 1 volt is input and output is 2 volt. When input is minus 1, input is 1 volt, output is minus 2 volt. It is inverted as well as amplified. Can you understand?
Yes. Yes. Here there is no role of reference signal, I think.
Sorry?
Here there is no role of reference signal. Input side.
Reference signal.
Huh?
No. We don't need reference signals because this. So the signal generator which I'm using, no, this one. This is just an input signal.
Okay.
Okay, this is input signal to this inverting amplifier. Okay, this is output. I don't need to connect this as output. Since why? Because I'm monitoring the signal output here only, not at this output stage. Okay, so without connecting the output, I can monitor the signal here. Okay. Any doubts? No. Okay. And I can use this IO cell also as input and output. If I select this as output, I can connect it here. Same output we can connect it to different IO cells. In all the IO cells, I can connect. Double click and select this as output. Again the same output only you'll get. Okay. Now I can use 4 probes. I told no. One more probe I'll keep it here. One more probe I'll keep it here. This probe I'll keep it here. Because since all the outputs are same, we have to put to all the IO cells. So we have to
Maximum of 4 channels, right? We can't go beyond 4 channels.
come again. I couldn't hear anything.
It is having maximum of 4 channels, so we can't go beyond 4 channels.
Beyond 4 we can't use. Inbuilt simulator we have only 4 probes.
But the IO probe you have given me total 7. So one probe is my input and I want to put electric input as my output, then I can't do that.
Yes, you can do. Like any port can be selected as input and as well as output.
But even if I will do that, I can't visualize that, right?
No, you can't visualize that. So no, if I select this as input, these wires are connecting, getting connected inside the FPA to these pins, right? IO pins. So if I select this as input, these top two pins will be connected, routed inside the FPA. If I select this as output, this bottom 2 pins will be routed to the FPA, inside the FPA. These are output pins and these are input pins. As I told, this is IO cell. So it can be input as well as output. These are output pins and these are input pins.
That I got. I I'm asking about the oscilloscope. We have display data as 4 channel only. So what I am asking, I can go beyond 4 channel or not?
No. You can't go beyond 4 channel.
That's what I'm asking.
No. Only 4 channels are available.
Okay.
Any other doubts?
No.
Nothing. Okay. Can see now the resources it is taking only 4 capacitors and 1 op amp it is taking to build this inverting amplifier stage. Okay. Now I will delete this. Okay. I'll use one more inverting amplifier.
What is the option for deleting? Just delete or
just click and delete. That's it.
Okay.
I'll use one more additional inverting amplifier. Click OK. Just I'll set the gain of second inverting amplifier as 2, same as first. I'll connect the input of this to this output and this output to these two IOCell. Now you can see what is happening. These two are getting clamped. Why? Now here the gain is 2, input is 1 volt, so output will be 2 volt. So here you are getting 2 volt as output. Okay. Again the 2 volt output is multiplied with the gain of 2. Okay. It is going above 4, until 4 volt. So I already said that FPA can work up to 3.3 volt. So operating voltage of FPA is 3.3. So since it is going to 4 volt, so the output is getting clamped. I'll keep this 1.5. Now you can see it is coming down again. So if your output is going above 3.3, so the output will get saturated. Okay.
Can you do that again? How you change the key?
Okay. Just click this.
Again.
Double click. And then just select and click to enter. And then click OK. Simulate. That's it. And again, if you want to change, double click. You'll get the window. Again, select 1, enter. And then click OK. That's it.
Means beyond 3.3 to be clean, no?
Yes, 3.3 will. So if it go more than 3 volt itself, it will start saturate.
Okay, beyond 3.3, it is
And the output will saturate.
Okay.
Okay. Any other doubts?
No.
Okay, can you try to do it yourself? The same thing.
Yes. Okay.
Can you share this? Share your screen so that I can see.
Just a minute.
Yeah. Okay. Take your time.
Okay.
No. Gain inverter. GAIN INV inverting. Yes.
Is it okay?
Right, is okay. You can change the gain and check.
Yeah, no, plus 3.0. Okay, if I want to do another inverting amplifier here, so can I copy this component?
Yes, you can copy. Copy paste.
Okay. Okay. Manage. If you are making it Control Z, Control Z. So, okay. Double multiply. Here are only 2.5 millimeters. 3.3 x. 3.0.2. That is 0.1. Okay, is that okay?
That's all. That's all. And one more circuit. Okay, you can see this. This is an oscillator. Okay, I'll do one more thing. And then okay, now if you see in this circuit, in this design, I have used 4 FPAs. Okay, this is FPA1, FPA2, FPA3, and FPA4. I have placed all 4 FPAs, but I have used only one FPA to build my circuit. Okay, this is oscillator. This is an oscillator. Oscillator sine wave. It can generate a sinusoidal signal. We can change the frequency and amplitude of the oscillator. Put my system. What I'm doing is here I'm just rectifying, full wave rectifier I'm doing. So you know full operation, you know the operation of full wave rectifier. So full wave rectifier nothing but it will convert the AC into DC. AC signals to DC it will convert. Okay. Now this is my this sinusoidal signal is the AC signal, right? I am feeding this AC signal to the rectifier. Okay. This is full wave rectifier. Just double click. If you go to library function, here you can see rectifier, half, rectifier filter, rectifier, like that. So if you see this, sorry.
Is there any search button for this component so that we can search and directly go through that component, or we have to search manually?
So search bar is not available. Like 49 components are there. You can just by name itself, you just simply read the name means you will get file get to know. There is no search available. Okay. So rectifier means rectifier half. Here it is. Like this you can. Okay. Now I have used the full wave rectifier. Okay. and the output of this full wave rectifier I fed it to the one more filter stage. Okay, so basic operation of the rectifier is it will convert the AC signal into DC signal. Okay, I'll simulate this. I'll turn this off. What is happening is, so this is out. This is my input signal, 100 kilohertz, 1.5 volt sinusoidal signal. I fed it to the rectifier stage. Input to the fed as input to the rectifier stage. So output of the rectifier you can. This is the output of rectifier. You can see. This is the output of rectifier. Since still my output signal has a AC components, so I want to filter AC components and make it a pure DC. So what I'm doing is to filter out the AC components from the signal. I'm using one more filtering stage. Okay. Now if I turn this on, so you can see. You see, this is my DC signal, DC output. First stage of filters, first stage filters output. Still some waves is there, still some AC components are there. So I'm using one more filtering stage. Now it is pure DC. Can you see? This is pure DC. DC signal I'm getting. So now the AC signal has been converted to DC signal using a rectifier, full wave rectifier, and 2 stages of filter. Okay. Now the simple AC to DC converter. Okay. What I'll do is, sorry, which filter? Filter biquad. Filter biquad 1. Okay. Filter biquad 1. And in this non-inverting type. In this non-inverting type, I'll give you the parameters also. Okay, I'll do one thing. Drive link I can share. I'll upload this file into my driver, and I'll share the drive link. Okay. You open it and read the parameters. Whatever the parameters I have fixed, read it and try to emulate the same. Okay. Can you give me 5 minutes? I'll upload and share the drive link.
Okay.
Just go through that rectifier circuit. If you have any doubts, just let me know. Just try to emulate the same circuit. Try to design. Keep it as a reference. Try to design the same by yourself.
I will not open it.
Just more apps. Click more apps.
Okay.
Come down. Browse. Look for another app in the PC.
And you have to choose the analyzing software.
Local disk C. Local disk C. Program files 86 it will be. Anadim. First one top. Anadim designer 2. Circuits. Program. Sorry. Back. Program. Select AD2. Open.
Okay.
Keep it as a reference and try to design the same. Just a rectifier. I explained, no? So in input AC signal, I will convert it into DC signal. 2 more filtering stages to make it a perfect DC without AC components. That's it.
ସେ କହିଲେ ମାନେ ଏଇଟାକୁ ଦେଖି ବନେଇବା ପାଇଁ ଚେଷ୍ଟା କର।
Now you got some idea about the tool, how to use the tool, right? How to operate.
Yes.
Our idea is to to give a hands-on about for this EDA tool. Like this technical details and all, right? So we can just study and understand. I will give you training about how to operate the tool. Okay. I shared you one more circuit, VC voltage controlled oscillator. Like try to understand the circuit, but Same folder I have shared. The drive folder.
So I designed the circuit as you have sent a copy,
Yes.
but I did it in the FPAA tool.
No
So
issues.
can I run on the FPAA tool or it's not possible?
No, you can use any FPA.
So how I will run this?
Like you placed all the probes. As I said, so we can use maximum 4 channels of, I mean, 4 probes only simultaneously. You used all the probes in FPA1. Okay.
Acha.
Now change it to FPA2. You can see the output.
And for example, upload कर दिया. Hello?
Hello. Now you double click that this VCO. Double click. Change it to 2000 kilohertz. Clock signal. Clock. Not this one. Clock frequency. You change, no? This gain inverter, no? Change that also to 2000 clock frequency. Okay. Now simulate. Why is this happening? Okay. You do one thing. You change, reduce the gain. Reduce the gain to 1.
Gain of inverter or
Gain of inverting amplifier. Again, it is same way.
but signal
10 microsecond only. Now you simulate the circuit which I have shared. Now you that green color channel is there, no? Green channel. Increase the voltage division to 2 per volts, 2 volts per division. Here in oscilloscope, increase to 2 volts per division. Okay. Now, if you change the gain of the inverting amplifier, you will see the change in the output. What is this? That white color cam is there, no? That main block. Hello, can you follow?
Yes.
Yeah, that white color block is there, no? Analog block, voltage controlled oscillator. So oscillator means it can generate any frequency. So voltage controlled oscillator means that oscillator frequency can be controlled with the input voltage. By using input voltage, by varying the input voltage, we can control the frequency of the output frequency of the oscillator. That's what this cam can do. Okay. So this oscillator can generate 2 types of frequency. One is 2 types of waveform. One is square waveform, and another one is triangle waveform. So that's why 2 output points are there. Okay.
Then why it is not coming?
Sorry.
Why it is not coming?
Why your circuit? Some mismatch it could be. Okay. This input voltage is there, no? You close this. 1.5 you keep. And input voltage then. Input voltage. This DC voltage. DC voltage cam. Double click. Make it negative. Okay. Now you simulate. Because output voltage you will get output. If your input voltage of VCO is positive, you will get some other voltage. If it is negative, you will get some other voltage. Since we are using an inverting gain stage, if you use positive voltage in the input stage, okay, So output of inverting stage will be negative. Okay. So this negative voltage I'm feeding, negative DC voltage of 2 volt I'm feeding. Again, it is inverted. So output will be positive.
Yes,
So
yes.
now we are getting this voltage. So like by varying the voltage sign or voltage value, you can change the frequency of the oscillator, output frequency of the oscillator. Understand? No? Any doubts on these all these circuits? You have any doubts in all three circuits? I mean, about the today's session. Okay, my idea is to give you some introduction about FPA, what is FPA, and applications of FPA, where it can be used. Okay, so morning we have seen what is FPA and how it can be used, different applications of FPA, and after that we have moved to software introduction. This EDA tool, how to operate the EDA tool, and how to create a simple circuit. And after that we have seen like how to design a simple basic circuits. 3 different circuits we have tried. So just a simulation hands-on, we have finished it. So far we have finished simulation part. So you tried 3 different circuits now. One is a inverting amplifier, and another one is rectifier circuit, a full wave rectifier circuit, and another one is voltage control oscillator. We have tried 3 different circuits in simulation. So the same circuits we will try with the hardware right now. So we can realize the output of the circuit in the hardware by downloading the code, whatever the circuit you have designed now. So by downloading the same code into the hardware, we can realize the output in real time. Okay. So before downloading the code into the hardware, let me explain the hardware first. What are the things available in FPAA tool? So can you show the hardware? Okay. And let me switch off the hardware first. This is FPAA quad board, we call it as. By quad board means it does have four FPAs. So we call it as FPAA quad development board. These are FPAs, U1, U2, U3 and U4 are the 4 FPAs, and this is a PIC microcontroller. So this PIC microcontroller is helping FPAA to communicate with the TC. TC means EDA tool through this USB connector. And it does have one power supply connector. You can feed a 5 volt adapter which comes along with this FPAA development. You can use that adapter to power up the board, and through this terminal block also you can power up the board. But so this is preferable. And it has 40 megahertz. It does have an inbuilt, onboard crystal also. It can generate a 40 megahertz. It can generate a frequency of 40 megahertz. But so far the hardware needs or FPAA needs only 16 megahertz. Okay. So this is a reset switch. So if you want to reset your hardware, you can use the switch to reset the entire hardware. And these are the communication headers. Communication is happening between the PIC microcontroller and all the FPAs. So once you remove these headers, so there won't be any communication between this FPA and this PIC microcontroller. Okay, so it should be on all the time. So we don't touch these headers and all, so jumpers and all. And these jumpers also should be there. So these jumpers make sure that interconnection between these FPAs, adjacent FPAs. This jumper is for connection between this FPA 1 and 2, and this for FPA 2 and 3, and this for FPA 3 and 4 respectively. And one more thing is these are the input ports. Input side, you can input side filter. The filters are available. Output side also some filters are available on board. Filters is whatever. So the input signal you are feeding. So the input signal also you can just filter, and after that you can feed into the FPA. So once input signal is filtered, you can feed the filtered input signal as an input to the FPA. And ADC channels are there. If you want to feed any input to the microcontroller, so this ADC signals are for these ADC channels are this ADC channel belongs to the microcontroller. You can feed any some input to the microcontroller, event based, input based communication from microcontroller to the FPA. because I told this microcontroller is communicating with the FPA. This microcontroller is sending commands to the FPA. We can give command to this microcontroller. So in such a way, this microcontroller can able to send a command to this FPA, all four FPAs. Okay. What we are doing is this: the controller is sending the command to the FPA, and we are just feeding input signals to the FPA through these red or here. Here you can see these are the I/O pins of FPA. You can see this. These are the I/O. Like you can see small holes on the board. So these are the I/Os of FPA. You can see I1P, I1N. So I1 means input, 1 means first channel, and P means positive. As I said, the FPA is based on differential architecture. So it does have one positive signal and negative signal as well. So you can see these are the I/O pins of FPA1, and this is the I/O pins of FPA2, and these are FPA3 and respectively for FPA4. These are the I/O pins. I'll explain the I/O pins in detail later. In hardware I/O pins in detail. And these are the supply and ground pins on board. So VDD is the supply and VSS is the negative supply. VDD is the positive supply, VSS is the negative supply, and these are ground pins. And 4 LEDs are there on board. 4 LEDs for indication when the program is happening. So whenever you are doing programming, that time this LED will blink, and once the program is finished, this green LED will blink. If there is any error in the programming, this red LED will blink. So different LEDs for different indication. So these are the features available in hardware, and this is one programming headers available. This programming header is to program the microcontroller. So like it's a JTAG for this microcontroller, big microcontroller. Okay. Now what we'll do? Yesterday we, the other day we did three simulation programs on that inverting amplifier.
Yes.
The same program will take up and realize. Dump it in the hardware. We'll see the output in oscilloscope.
Okay.
Like have you saved the design, that inverting amplifier design the other day?
Let me see.
That's it. Now you go to hardware. Switch on hardware once.
Sorry.
Your hardware FPA board.
Yes. Okay. Is it visible to you?
It is visible now.
Okay.
Now you connect the USB cable. USB is connected, right?
Yes.
Now you power on the board. Connect the power adapter. Once this is on, now check with the EDA tool whether the connection has been is available.
Which connection?
Communication is available. Communication between board and the EDA tool.
The green LED is glowing.
The port settings you should check.
Port setting. Where we can check that?
Go to the EDA tool. Settings.
Preferences. Okay.
Port 5. You verify it through device like
From device manager, right?
Device manager. Ports. COM port 5. I use the same COM port in the EDA tool. Apply OK. Now you check for target.
Target. Okay.
Display board. All 4 FPAs are communicating with the EDA tool.
Suppose one of the
Communicating.
FPA is not communicating, then how we will get that? This 1, 2, 3, 4 will be the arrangement is different.
So once the board is connected, no, all 4 FPAs will detect all the time.
Mm-hmm. Suppose in case of one FPA, one FPA is not connected, then how in this window we will identify that? That's what I'm asking.
It won't happen that way. Either all 4 FPAs won't, the board won't get detected, or it will get detected.
Okay, okay.
It doesn't work that way. Like either one of the FPA doesn't work. It doesn't work. It will never work that way.
Okay.
Either of the FPAs are getting detected means there is some issue between the connection. Like a USB cable is there, some issue between the connection.
Mm-hmm.
Both it be wrong. Okay.
Okay.
Now one more thing. So in EDA tool, you are using FPA1 alone, right?
Yes.
Okay, but in hardware you have 4 FPAs, FPA1, 2, 3, and 4,
Mm-hmm.
right? Okay. Now if you the design circuit which you have designed no in EDA tool, so if you dump that circuit into the hardware, only one of the FPA, I don't know whether which FPA will get loaded. I mean, it should be like it doesn't mean I don't know. That FPA1 is there on hardware.
Mm-hmm.
So if you use the whatever you are having no same circuit in the ADA tool, if you load the same circuit in the FPA board, only FPA1 will get loaded. Okay, all 3 FPAs, the FPA2, 3, and 4 will get the empty configuration, okay, null configuration. Okay, we can't send the null configuration, empty configuration to the FPAs. Okay, all 4 FPAs should get some configuration. I mean, it doesn't mean it should have some circuit. All 4 FPAs should have some circuit. So you should place at least the plain FPA, I mean empty FPA in the area tool also. Okay, we can't send the empty configuration to the FPA, any of the FPAs.
Sir,
Can you understand my point?
no, sir. If you
Hello.
no, sir. If you repeat once again, then that will be better.
I'll repeat it. In your area tool, you are using single FPA, right? In your EDA tool, until to go back to EDA tool.
Tools.
You are only one FPA. No, let it be. This one is the EDA tool, FPA. Let it be. Don't go for any. Okay, you are using single FPA only.
Yes, sir.
FPA1 only you are using.
Mm-hmm.
You are having circuit inside the FPA1. Okay, but in hardware, FPA is on board. FPA1, 2, 3, and 4. That is U1, U2, U3, and U4.
Mm-hmm.
Okay. So if you can circuit only with the FPA to hardware, see that FP1 on the hardware, U1 on the hardware will get loaded. Other 3 FPAs, U2, U3, and U4 will get the empty configuration.
Okay. And what is empty configuration?
We'll get the empty configuration only since we don't have any circuit in the area tool for FPA 2, 3, and 4.
Mm-hmm.
Okay, FPA we have a circuit. Okay, if you send the same, if you load the same circuit into the hardware, FPA 2, 3, 4 will get the empty configuration. So the circuit won't work.
Mm-hmm.
So what we should do is at least an empty FPA chip in the area tool we should use for FPA 3 and 4. You don't need to design any circuit for that. Just empty FPA chip inside the area tool for FPA 2, 3, and 4 to avoid that the FPA 2, 3, and 4 is getting loaded with the empty configuration. So you choose simulator once, simulator window.
This one.
Simulator window. No. Simulator window, you close it. Close it. Not this one. You close the circuit, right?
Okay, we are asking to close this one.
You close the simulator window alone, not this one. Simulator window alone.
Okay, I got it.
Plus window is there, na? That one. Okay. Now you right click,
Here.
not inside the FPA, outside the FPA. Right click,
Hmm.
insert new chip. Insert new chip. Choose the correct part number.
This is 4 means AN231E02. AN.
Select it and place it near FPA1. Okay. Same way FPA 2, 3 and 4 you need to place.
Okay, I got it.
If case
Okay.
you can just copy it or do the same way. Right side. Right side. Yeah. You should have some space in between. That's it. Now you check the board information, you target. Target board information.
Okay.
All four FPAs are detecting. Okay. Now we can download that. So we should download the circuit into the FPA hardware. Okay. How we go to configure. In the area tool itself, configure. Right configuration data to serial port. Now the LED on the hardware will glow like a blink.
Yeah.
That green.
The orange color LED on the hardware, right?
Now press Control W on the keyboard. Control W. Let the camera window be open. Let the camera window. And press Control plus W on the keyboard. Now the yellow LED will blink 4 times and green LED will stand by. Control W. When you are on the area tool. Control W. Now the yellow LED was blinking 4 times, right? Yellow LED was blinking 4 times. After that, green LED standby. Okay. Means that why the yellow LED was blinking 4 times means that all 4 FPAs are getting loaded.
Can we do it once again? Because we want to see once.
Yeah, do it again. FPA3 did not configure properly. Check the connection once again. You open the area tool window. Click OK. Target. Now you do it again. Download now the configuration. Do it again. It is working, right? Yeah, okay. Now the board is configured with the circuit, with this circuit. Okay. Now what we can do is we can take the output in the oscilloscope.
From the circuit itself, from the board itself.
Hardware. Yes. Now you open the hardware window. Camera window. Okay. You have probes, right? Probes with the jumper cables.
Yes.
Yeah, you take the probe and jumper cable.
Sorry, sir.
Probe with the jumper cable.
Okay. Yes, sir. We are having the probe right now.
You connect it.
And where to connect? The oscilloscope is already connected with the probe.
Oscilloscope is already connected, right? With probe. Okay. And connect the jumper cables with the probe, like positive and ground terminal.
Yes.
Connected, no? And connect the positive terminal to FPA1.
At which point?
FPA1. FPA1, I'll tell you the point. Go to the EDA tool once. EDA tool window. Now, where you have connected the output now? IO cell.
IO3. IO4.
IO. No. Check once again.
IO3.
IO cell 3. IO cell is configured as output. Right? Now go to the hardware, camera window.
Yes.
If you check the hardware, okay. Below U1, below U1 IC, FPA1 is there, no? FPA1. FPA1. That one is FPA1, right?
Yes.
Okay. I told you know the IO pins of FPA1, FPA2 respectively.
This side.
It was like U shape, in U shape. Okay. In right side corner, that U shape pins are there, no?
U shape
around FPA. U shape around FPA. I'll tell you. I'll show you my screen.
Yes, sir.
Here. You see? Sir, IO pins. Okay.
Yes.
Yeah, these are IO pins. If you check this, you configure this FPA1 as output, right? Okay.
Yes,
So FPA1 IO cell 3 as output. Okay. So 3P. Here it is. This is the right side.
3P.
Right side.
3P.
Bottom two pins.
Yes.
O3P and O3N, which means output third IO cell positive pin and output third IO cell negative pin.
Okay.
And again, if you go input third IO cell negative pin, input third IO cell positive pin. So respectively, all the IOs will have the numberings in a similar way.
It means, sir, for the total number of 6 IO pins, there is a 6 into 4, 24 combination for input positive negative and for output positive negative, right?
Not 24 combinations. Okay, first IO cell 1, 2, 3 and 4, all 4 will have four pins. Separate pins for input and separate pins for output. And the remaining 5, 6 and 7th IO cell is there, no?
5, 6, 7, yes.
IO input and output pins are combined. So two pins for both IOs. Both input and output as well. The first 4 IO cell will have a separate input and output pins, and the 5, 6 and 7 will have a same input and output pins. It can either be configured as input or output.
Okay.
In IO cell 1, 2, 3 and 4 cannot be configured as input and output simultaneously. It can also be configured either as input or output, but it does have a separate pins. But in IO cell 5, 6 and 7, it does have a same pins.
Why?
Okay, it's sharing the input and output pins. That's it.
Not
Not
why
much.
that is so?
Sorry?
Why it has been done in that way?
No, that is for internal how can I say, internal design purpose. They have made it in such a way.
Okay.
No, any function unknown. Not depends on the functionality. So internally, for a design purpose, physical design purpose, they have made it in such a way.
Okay. So here you are saying that for the output 3 pin, we have to connect one probe at the IO3 positive and the second probe at the IO3 negative.
At the output 3P, oscilloscope ground at output 3N, O3N. Can you share your camera window?
Okay.
Oscilloscope positive pin at O3P.
O3P, yes.
Oscilloscope positive at O3P and oscilloscope ground at O3N.
Okay. Oscilloscope positive at O3P and oscilloscope ground and O3N. Ground tala negative, positive tala positive.
Yes, yes, yes.
एंड ହେଲା ଗ୍ରାଉଣ୍ଡ କହୁଛ ଏଟା ଏଠି ଯୋଉ ଗ୍ରାଉଣ୍ଡ ଗୋଟେ ଅଛି ଏଇ ଗ୍ରାଉଣ୍ଡ କାହାର ଏଇଟା କାହାର ଏଇଟା
Sir. Sir.
Tell me.
Sir, there is two other pin as G and D ground and VDD power supply. So in this case we are taking negative as the ground, then why the ground and VDD is given?
No. What is happening? No. So we are providing a supply as single-ended supply. Okay. Internally, the FPA is converting the single-ended supply into negative. Okay. I mean a differential one. Okay. For else we should give a negative supply as well.
Okay.
Here, if you
so
see,
since our design is based on a differential signal, that's why we are taking negative as
differential
ground and
architecture,
positive at
internally
positive.
yes, of
And
course.
okay.
So if you see, I told no that below the FPA2, U2 and the U3, so VSS pins will be there, ground pins will be there, and VDD pins will be there. Can you see?
Sir, can you repeat?
Below U2 and U3 IC, okay, there are sections of pins like named as VSS, ground, and VDD. Below U2 and U3.
U2 कोड U2 3 कोड
FPA2 and 3. Below FPA2
this one
and 3.
VSS ground
VSS,
VDD
ground. That VDD is a positive supply and ground is a zero reference, and VSS is a negative supply. If you measure, you will get minus 3.3 volt in VSS and plus 3.3 volt in VDD. So internally that positive supply has been converted into negative and it has been taken out for user purpose. Okay.
the positive supply negative supply ground
Okay, now you forgot everything. Now simply you connect O3P to the oscilloscope probe positive pin and O3N to the oscilloscope ground pin. That's
Negative pin.
Let us check the output first. We will proceed further. I mean, later doubts and all we will clarify. We'll see.
Positive हाँ direct connection.
ଏଟା ଜିନିଷ ପାଇଁ କେମିତି ଏଟା ତ ଡାଇରେକ୍ଟ
सोसिया पे पड़
ପଚାର ଦେବ ଏଟା ତ ଢିଲା ଅଛି କନେକ୍ସନ ନା ଏ କନେକ୍ସନ ତ ଲୁଜ ରହୁଛି
जंपर केबल होगा ठीक से देखिए एक ठीक से हाँ सेंटर लूज रहेगा
को कनेक्शन लूज रहुଛି ବୋଲି
sir
और जंपर केबल डालो
Yes.
Where we are inserting the
wires
jumper wires, we feel the connection a little bit loose. So is it okay or?
No. It will be like that only because the whole size is little bigger no than your wire thickness.
Okay.
That is
Okay.
so it will not impact the reading
not a concern, not an issue.
It will not affect the reading.
No. It won't affect it. And sometimes like sometimes your output may not come. Like you should hold it. Sometimes you should hold it. That's
No,
it.
but if we have a larger number of input and output, how we can hold all the wires and take the output?
No, you don't. You can just adjust and keep it as it is.
Okay.
That's it. It won't affect it.
Okay, let us check.
As
this is
you let us. Let's
କୋଡ ଦବା ସେଟା ଦବା
ଦୁଇଟା ଅଛି ସେମିତି କାହିଁ ଅଛି ଏମିତି କାହିଁ ଅଛି
The negative. The negative. This is positive. Positive, where is positive? Positive. Discussion.
So we have connected the probes.
You connected the probes, right?
Okay, you
Okay, you press auto set in oscilloscope.
offset, auto set.
Yes. Yes. H. You connected. I mean, your probe is connected to channel 1 or 2?
Channel 1.
Channel 1. You switch off the channel 2 then? That blue one? Okay. Now you do one thing. Open the EDA tool and change the gain.
Change the gain. Okay.
No. In EDA tool.
Got it.
Now download the circuit again. Configure. Camera window. It is changing, right?
Change the auto setup.
It was changing or what?
I didn't.
Change means what?
Gain change the waveform to change.
The output signal amplitude was changing or what?
No.
No, it was not changing. Okay.
I think
Let
it's
me change. Let me do it 1 second.
No. Wait. Open the camera window. Okay. Reset button is there, no, on board. Reset button on board. On FPAA board.
Yes, this one.
Yes, you press it once. No, it is not changing. You are not getting the proper output. Delete IOSL 3. I mean, IOSL 3 you delete once. IOSL 3 connect to oscilloscope. I mean, sinusoidal output. Sinusoidal output. Sorry. No. Output side. You are connecting to input side. Okay. Now you configure and do it. No, do it again. Check target and do it again. Now do it again. Press Control W, Control plus W, that's it. Now you go to camera window. Are you getting any output?
No.
No. Not getting any output. Like what is the settings like? Can you tell me the oscilloscope settings? Voltage per division?
2 volt.
2 volt.
2 volts. Make it 1 volt. And time division?
2.
2.5
Time division?
2.5 millisecond.
2.5 millisecond. Make it 10 microsecond.
Setting this.
No, that is position. Make it 10 microseconds. Not that one. That is voltage per division. Make it 1 volt. Third one. Like 1, 2, third knob is there, no? Above the oscilloscope, that one. You try that one. It is time, whether it is time division or not. Changing, no? Make it 10 microseconds.
माइक्रो 500 अच्छे तो 10 कर
कितने करीब
10
Green color LED is glowing or not in the FPA board?
yes it is glowing
As it is glowing, right? Okay.
डायरेक्ट कितने हो चुका था 1 मिलीसेकंड
Now press auto set once in the oscilloscope. Okay. Now you remove the probe positive from the board. Now you insert again. Now change again. No, change again.
yeah it is changing
It is changing, right?
yes
Okay. Issue with the probe cap only. It was catching some noise. The probe cap is there, no?
बट रिजल्ट शो करो मैं ठीक से पिक टू पिक 3
Change the voltage per volt. Voltage per division. Where you connected the probe, 1 volt. Okay. We'll do one thing. In oscilloscope probe is there, na? That attenuator adjustment will be there. 10x and 1x adjustment will be there. Make it 10x.
नहीं actually here it is not there
No, not in that. I'll show you.
इतने नहीं सेटा पोल्स
Here it is. Like this one.
नहीं
no but in our probe the probe adjustment attenuation setting is not there
Oh, adjustment setting is not there.
yes
Okay then. Okay, let it be. Okay, you're getting output, right?
yes right now yes
Yes. Okay. Now this is static configuration. Okay. So suppose if you want to change gain means again you have to go back to the EDA tool and change again. Re-download the circuit again into the hardware.
वोल्टेज
Okay.
शो करो
This is static configuration.
वोल्टेज
Whenever you want to make changes in the parameter of the circuit, you have to re-download the code. Make changes in the circuit, re-download the code. This is static configuration. So I told no dynamic reconfiguration. So without re-downloading the code again and again on the fly, okay, you can modify the circuit parameter. That is dynamic reconfiguration. Okay. So dynamic reconfiguration example I'll show you in the afternoon.
okay
So as I said, so till 1 o'clock you will be available, right? After that 1 o'clock you will be having lunchtime, right?
yeah once 1 to 115 120 also we can be here
No issues. We'll do one thing. So we have finished this example, right? That rectifier circuit, right? Rectifier circuit.
yes sir
Rectifier circuit. Download that rectifier circuit in the hardware and check the output in oscilloscope.
प्रोटा कौन আছে
ठीक है सर
अबे ठीक होगा 3 4 जगह 4 4 रे कनेक्ट
पिक टू पिक अच्छे ना एटा चैनल पिक टू पिक 3.24 अच्छे
कितने में करता
4 है बात
एम्पलीट्यूड 1.5 अच्छी तो
1.5 अच्छे तो ठीक अच्छे
3 है बात पिक टू एम्पलीट्यूड चेंज करेंगे देखियो 0.5 कर दीजिए
कल कितने कल
1
2 एस्ट
ठीक আছে बट हम फुल वेव रेक्टिफायर यूज करছি কিছু চেঞ্জ হবে না हाफ वेव कर दीजिए पॉजिटिव हाफ कर दीजिए देखिए कौन আসছে
टू पॉइंट 1.6
চেঞ্জ হওয়ার কথা না ফুল ওয়েভে যেটা আসবে পজিটিভ হাফ তো খালি ফার্স্ট পজিটিভ হাফটা আসবে কথা
लगे तो फिल्टर सेट देखा सेट सिग्नल देखला सेट सिग्नल देखा
अच्छा हाँ এটা আসছে
आउटपुट देखो हम आउटपुट देखछन ना हां
ओ हाँ हाँ मैं आउटपुट देखছি हाँ यस 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 देखिए ये कोटा येलो हाँ येलो तो अलग कुछ है
आप जो प्रिंटर से तो कोई से कनेक्ट है
ये मानो शांति ये टाइटा ଆମେ ଏଇଟା 04 ରେ ଦେଖି ପାରିବା ଏଟା ଯୋଟା ଆସୁଛି ଖାଲି ଇନପୁଟଟା ଆସୁଛି ବୁଝିଲେ ଏଟା ଆମେ ଇନପୁଟଟା କନେକ୍ଟ ହେଇଛି ନା पोर्ट 3 ସହିତ
हमें इनपुट देखछन
हां आउटपुटटा 4 रे आसी
आउटपुट देखियो आउटपुट को पिन
4
आउटपुट 4n आउटपुट 4p p is positive बिल्कुल हल्ला कथा नहीं है कौन
मते कम वैल्यू बोली जाना पड़नी सेंती लागो
केते कम वैल्यू कौन था वैल्यू केते
एटा आउटपुटटा येलो कलर
मिली वोल्ट देखो फ्लक्चुएशन କେମିତି ଅଛି?
फ्लक्चुएशन तो इधर भी अच्छा इनपुट भी अच्छा
पिंगटा कौन?
अच्छा रहंतु मु या कनेक्ट करू छी आउटपुट रे
follow the
ये देखिए
Hello.
हाँ सर आसना yes sir
এটা kind হলুছ
Yes.
we are getting the output right now with the new probe we have changed so we have checked the input
Okay.
here and I just make some modification in the circuit to better visualize the output so this is the input port this is the output
You need to visualize the output.
yes right now it is output
आउटपुट एम्प्लीट्यूड केते अछि एम्प्लीट्यूड केते देखा तो 1.2 अछि 1
half visible
Okay. Can you share your camera window? Let me see.
yes এইটা আছে লুজ কানেকশন পাই
hello
Yes.
कौन कहउछन से
hello sir are you there
Yes. Yes. I'm here. Tell me.
you told me no, to show the output no
Yes.